Right now, there is a single building on the planet, not a government, not a military base, not Wall Street, one building that if it burns down tonight, the entire global tech industry collapses within 3 years. No more iPhones, no more AI, no more modern weapons guidance systems, no Netflix, no GPS.
Not because of a cyber attack, not because of a war, simply because one company in one small Dutch city most people couldn't find on a map makes the only machine on Earth capable of printing the chips that run our civilization. And here's the terrifying part. There is no backup plan.
This is the story of ASML, the most important company in the world that almost no one has ever heard of.
To understand why this building matters, you first need to understand what's built inside it. Every computer chip and every device you own is manufactured using a process called lithography. Think of it like a camera. You project a pattern of light onto a surface coated with a light-sensitive chemical, and that pattern gets etched into silicon, forming the microscopic circuits that make computers compute.
Simple idea. Except the circuits on a modern chip are almost incomprehensibly small. A human hair is 80,000 nanometers wide. The transistors inside the chip powering your phone right now are approaching 2 nanometers.
For scale, that's like trying to print the complete works of Shakespeare on a grain of rice using light. Normal light can't do this. The wavelengths are too long. Physics says no. So, ASML invented a different kind of light. Inside an ASML machine, a droplet of liquid tin, smaller than a human blood cell, is fired into a vacuum chamber at high speed. A high-powered laser then hits that droplet 50,000 times every single second. This vaporizes the tin instantly, creating a plasma that reaches 220,000 degrees Celsius, hotter than the surface of the sun by a factor of 40. That plasma releases a flash of extreme ultraviolet light, EUV, with a wavelength of just 13.5 nanometers. And that flash is what prints the world's most advanced chips. The machine that does all of this is the size of a city bus. It weighs 180 tons. Shipping one requires 7 Boeing 747s or 25 cargo trucks. It costs up to $380 million, and only one company on Earth knows how to build it. ASML ships roughly 40 of these per year. Every single advanced chip made by Apple, NVIDIA, AMD, Qualcomm, every chip powering AI data centers requires one of these machines. There is no alternative. There is no workaround. This is not a market advantage. It is a law of physics. ASML was not always this powerful. In fact, when the company was born in 1984, it was a corporate joke. Philips, the Dutch electronics giant, spun off a small joint venture with a firm called ASM International. They literally set the new company up in a leaky shed behind the Philips campus in Eindhoven. No market share, no revenue. Their main competitors, Japan's Nikon and Canon, were already billion-dollar titans with decades of experience. ASML had a broken coffee machine. But one decision in the early 1990s changed everything. The industry faced a critical fork in the road, 2 competing approaches to how machines would expose light onto silicon. Nikon bet on the simpler path. ASML chose the harder one. ASML was right. That single technical call shifted the ground beneath every competitor in the industry. Then came the masterstroke. In the early 2000s, ASML launched what they called the Customer Co-Investment Program. The pitch was blunt. If you want the next generation of machines, you have to help us build them. Intel, TSMC, and Samsung collectively poured $4.1 billion into ASML's research and development. In exchange, they got early access to the hardware and seats at the table shaping where the technology went. On the surface, this looks like a funding deal. In reality, it was an economic trap for everyone else. By writing those checks, the 3 most powerful chip makers on Earth had tied their own survival to ASML's success. Walking away would have meant burning billions in sunk costs. And because they sat at the top of the manufacturing pyramid, their commitment sent a signal to every other buyer in the world. The competition
is over.
Nikon and Canon never recovered. By 2019, when EUV machines finally hit factory floors at industrial scale, the entire global semiconductor ecosystem had been built exclusively around ASML, and their rivals had been structurally eliminated.
You cannot buy 40 years of trial and error. That knowledge doesn't live in a manual. It lives in the institutional memory of thousands of engineers who have spent their entire careers solving these exact problems. That is the moat. And it was built not by lawyers or lobbyists, but by the passage of time itself.
The machine is only half the story. To build a single EUV system, ASML must coordinate over 100,000 individual parts from thousands of suppliers across dozens of countries. But unlike most global supply chains, which have redundancy built in, ASML's has almost none.
At the most critical points, there is one supplier, one source, no backup. The mirrors that guide EUV light are among the most precisely engineered objects ever created by humans.
Each one is built from 130 alternating layers of silicon and molybdenum, every layer just a few atoms thick. If you scaled one of these mirrors to the size of Germany, the tallest surface imperfection would be less than 1 millimeter high.
Only one company on Earth can make them, Carl Zeiss SMT in Germany. ASML eventually acquired nearly 25% of Zeiss's optics division, not as an investment, but as a defensive maneuver to ensure their sole mirror supplier could never be bought by a rival nation.
The laser that vaporizes those tin droplets is made exclusively by Trumpf, another German company. It took nearly 20 years of continuous refinement to reach the power and pulse precision EUV demands. No other manufacturer comes close.
And the light source itself, the technology controlling the laser-tin interaction, was originally developed by an American company called Cymer. ASML acquired them in 2013 for $2.5 billion and brought it fully in-house.
Germany provides the mirrors and the laser. The US and Netherlands provide the light source. Final assembly happens in one building. Veldhoven, one coordinate on a map.
If you want to disable the entire global semiconductor industry without firing a shot, you don't need to bomb Taiwan or hack Wall Street. You need to close one building in a Dutch city of 45,000 people.
Governments figured this out, and they moved fast. In 2018, US officials applied direct pressure on the Dutch government to stop ASML from exporting its most advanced machines to China. The legal mechanism was a routine Dutch export license. The strategic impact was anything but routine. In 2019, ASML's license to ship EUV machines to China was quietly allowed to expire. No press conference, no sanctions announcement. One administrative decision rewrote the semiconductor map of the world. By 2023, controls had expanded to cover older deep ultraviolet machines as well. China had lost access to the cutting edge. Now they were losing access to the tools needed to stay in the game at all. Meanwhile, ASML's campus in Veldhoven had already become one of the most actively targeted industrial espionage sites on the planet. In 2018, a former employee was caught stealing source code and technical documentation linked to a Chinese-backed chip firm.
Dutch and American intelligence services had flagged the building as a top priority target for foreign collection operations. But here's why the espionage still can't work. A stolen blueprint is not a machine. The machine is the product of 30 years of institutional knowledge distributed across a network of partners on 3 continents. You cannot photograph a manufacturing process and expect to reverse engineer EUV from an image.
China's official answer is yes. Beijing has set a public goal, a working domestic EUV machine by 2030. Almost every independent expert views that deadline as a political statement, not an engineering roadmap. The physics alone explains why.
EUV light is absorbed by almost everything it contacts: air, glass, water vapor, trace contamination. You can't focus it with a normal lens. Even a few stray air molecules in the beam path destroy the signal.
The entire optical path must exist inside a near-perfect vacuum. The mirrors must be polished to a surface roughness below 0.1 nanometers. That's not an ambitious manufacturing standard. It is a hard physical threshold. Fall short by even a fraction and reflected light loses coherence. The chip fails every single time. And then there's the problem no amount of money can solve: institutional knowledge. ASML employs thousands of engineers who have spent their entire careers mastering one narrow subsystem of one machine. That knowledge isn't written down. It lives in how they diagnose a failure at 2 a.m., in the cross-team relationships built over 15 years of shared problem solving.
You cannot hire that. You can only grow it. And growing it takes time that no government deadline can compress.
The most credible independent estimates put a minimum of 15 to 20 years on any serious attempt to replicate EUV from scratch, and that assumes access to the same global supply network that export controls have already placed out of reach.
We don't need to imagine what a disruption looks like. We already lived through a preview. In 2020, COVID-19 slowed ASML's assembly lines.
Machines scheduled to ship in one quarter didn't leave the dock until the next. A delay measured in weeks echoed across the entire global economy.
By 2021, that single slowdown had become the worst chip shortage in modern history. Ford, GM, Volkswagen, and Toyota all idled factories because they couldn't source the microcontrollers to finish their vehicles.
The automotive sector alone lost an estimated $210 billion in production value. Medical device lead times exploded. Defense contracts slipped. That was a slowdown, not a failure. One building, running slower than usual, cascaded into a global economic crisis. Now consider this. Every EUV machine ever delivered was assembled in one building on the ASML campus. No second facility exists anywhere on the planet. A fire, a flood, or a precision cyber attack on that facility's control systems wouldn't slow EUV production. It would stop it completely. And the waiting list for these machines already stretches years into the future. Meanwhile, governments are spending hundreds of billions building new chip fabs in Arizona, Germany, and Japan to reduce dependence on Taiwan.
But here's the paradox they haven't solved. Every single one of those new fabs still needs a delivery from Veldhoven before it can produce one advanced chip. Geographic diversification of fabrication doesn't dissolve the ASML dependency, it deepens it. More factories, same one source. ASML's current market cap exceeds